In this video, we're going to look at how the derivative affects the shape of a graph. What does the derivative of a function tell us about a graph? If we have some function and we look at the derivative of this function on, let's just take this interval from a to b. What could we say about the derivative of this function since this function is increasing? Well, we could see that the slope of the tangent lines would always be positive. Let's look at another function. Here we're also increasing, and also the slope of the tangent lines are positive. So if a function is increasing, we should know that the slope of the tangent lines are positive. And likewise, if a function is decreasing, we can see that the slope of the tangent lines are going to be negative. Again, here we would have slope of our tangent lines. Those would be negative values. So the derivative of a function tells us where the function is increasing and where it is decreasing. So here's the graph. Here's a graph of a function. And notice from a to b, the function is increasing. So the slope of the tangent lines will be positive from a to b. From b to c, we can see the function is decreasing. So the slope of the tangent lines are negative. And from c to d, again, the function is increasing. So the slope of the tangent lines would be positive. So if we draw the tangent lines in, that confirms our result. Those are negative, and now they're positive again. That leads us to the increasing-decreasing test. If f prime of x is greater than 0 on an interval, which means the derivative is positive, then f is increasing on that interval. Part B says if f prime of x is negative on an interval, then f is decreasing on that interval. Find where the function 3x to the fourth minus 4x cubed minus 12x squared plus 5 is increasing and where it is decreasing. So just from those previous slides, we should be thinking we have to determine where this function, the derivative of this function, is positive, because we know if the derivative of the function is positive, it's increasing, and we have to look at where the derivative is negative, and that will tell us where it's decreasing. So let's look at the derivative of this function. But before we do, let's just discuss something quickly here. If I'm increasing on this interval from a to b, from a to b, we can see the slope of the tangent lines would be positive. Now, what would happen right here at b? Well, it appears we have a tangent line that has a slope of 0. Notice the tangent lines from a to b, they're a little steeper here than here, and so the slope of those tangent lines are getting closer to 0. Now, when we hit 0 here, we can see that if we proceed from B to C, the slope of the tangent lines are now negative. And when we get to C, again, the slope of the tangent line equals 0. So it appears that before we change from positive to negative, the slope of those tangent lines, when we change from positive to negative, the slope of the tangent line has to be 0. Same thing occurs here. Here we're negative from B to C, but at C we're 0, and we're changing from negative slopes to positive slopes. So that may indicate when we find the derivative of the function, if we set the derivative equal to 0 to find these values where they change, now they don't have to change there, but if they do change direction, it would have to occur at these points. So let's set the derivative equal to 0, and then we can find these values where the slope of the tangent lines are 0, and then we can analyze if the slope of the tangent lines change. Then we can determine if they're positive or negative, and we can then determine the intervals where it's increasing and the intervals where it's decreasing. So f prime of x equals 12x cubed minus 12x squared minus 24x. And we said we're going to set the derivative equal to 0. Let's factor out a 12x. So we'd have x squared minus x minus 2. Let's see if this is factorable. We'd have x here, and this would be negative 2, positive 1. We'd get x squared minus 2x plus x gives us negative x, and then 1 times negative 2. So if we set each one of these factors equal to 0, we get x equals 0, x equals negative 1, and x equals 2. Let's draw a number line and put these values on our number line. And you can see we're creating these intervals. Let's look at those intervals. The first interval would be from negative infinity to negative 1. The second interval is negative 1 to 0. Third interval, 0 to 2. And we've created a third interval, 2 to infinity. Now, on these intervals, could the derivative change within one of these intervals? Well, the answer is no. If it did change, it would have to go through 0. So we are assured whatever is happening with the derivative on these intervals, it's going to stay the same. So we can choose any value that we want in any of those intervals to plug into the derivative to see if the derivative is positive or if it is negative. So let's take this first interval. I'm going to take and plug in negative 2. Now I don't want to take negative 1 because I know I would get 0. So I can take any other value in that interval. I'm just selecting negative 2. And if we plugged negative 2 back into the function, we want to know if this function, if the derivative is positive or if it's negative. Now what I like to do, I don't care about the value, I just want to know if it's positive or negative. So I'm going to go back up to the factored form of the derivative, And if we plug -2 in, you can see here for 12x, we'd get a negative value. If we plug -2 into x plus 1, we would get a negative value. And if we plug -2 into the third factor, we'd get -4, which is a negative value. So we would have a negative times a negative times a negative, which would give us a negative value. So we know that the derivative is negative on this interval, so the function is going to be decreasing. Let's take the next interval. So into the derivative, we're interested to see if the derivative is positive or negative. So we have to choose a value between -1 and 0. So let's choose -1/2. If we plugged -1/2 back into the derivative now, we want to know if the derivative is positive or negative, so we're plugging these values back into the derivative. If we plugged a -1/2 into 12 times x, we would get a negative value. If we plug -1/2 into the second factor, we would get a positive value. We'd get +1/2. And if we plugged a -1/2 in for the x in the last factor, we would get a negative value. So we'd have a negative times a negative, which is a positive number. So in this interval, we know the function is increasing because the derivative is positive. Next interval, we're going to choose a value to plug into the derivative. Let's just choose 1. And again, we're going to analyze the derivative at that value. So if we plugged 1 in, 12 times 1 would give us a positive value. 1 plus 1 would give us 2, so we'd have a positive value. And then if we plugged 1 in for x in the last factor, we would get -1. So we would get a negative value. So a positive times a negative gives us a negative value. So we are decreasing on this interval. Our last interval, I'm going to choose 3. And let's analyze what's going on with the derivative when x equals 3. So if we plug in 3, 12 times 3, that would give us a positive value. 3 plus 1 is 4, so that's a positive value. And 3 minus 2 also gives us a positive value. So a positive times a positive times a positive. Our function is going to be increasing on this interval. Now let's just do a little bit more analysis on this. If we have this function and from -infinity to -1, we know it's decreasing. So let's say this is -1. We know the function is decreasing, but then at -1 it changes to increasing. Then it's increasing all the way to 0. But then at 0 to 2, it's decreasing. And then from 2 on, it's increasing. So can we determine if we have local maximum and local minimum values just by looking at our chart, determining if the derivative is decreasing and changes to increasing or vice versa. So on the interval negative infinity to negative 1, we're decreasing, but then we change to increasing. So we can see from the graph, if we're decreasing and we change to increasing, we are going to have a local minimum. Then from negative 1 to 0, we see we're increasing, but then we change to decreasing at 0. So we will have a local maximum at 0. And then from 0 to 2, we're decreasing, and then after that, we're increasing. So we would have a local minimum at 2. So not only can we tell where this function is increasing and decreasing, we can determine if we have local maximums or local minimums at those values. Now let's take, for instance, the interval from negative infinity to negative 1. That's decreasing. What if on the interval negative 1 to 0, it was still decreasing? We would then not have any local maximum or minimums. The sign of the derivative needs to be changing in order to create a local maximum or a local minimum. Now, the top of this slide shows you the technique that I used. I like using the number line and setting up the critical numbers on that number line. The table below that is just another way to organize your information. It does give us the same intervals. You can see here's the interval from negative infinity to negative 1, which is this interval here. X is less than negative 1. And then it's just like we did, we're determining if we plug in a number on that interval into our factors, we're then looking at is the derivative positive or negative. And then we make our conclusion. If it's negative, we say it's decreasing. Here's the function that we just worked with. We can see it's decreasing on the interval negative infinity to negative 1, increasing negative 1 to 0, decreasing from 0 to 2, and then it is increasing from 2 to infinity. Now notice when we write the intervals of increase and decrease, we do not include those endpoints. It's neither increasing or decreasing at those endpoints. So we use open intervals, not closed intervals, to describe where the graph is increasing and where it's decreasing. First derivative test. Suppose that c is a critical number of a continuous function. If f prime changes from positive to negative at c, then f has a local maximum at c. This is what we were discussing in a previous slide. We can determine if we have local maximums or local minimums by looking at our chart and determining if the derivative changes from positive to negative or negative to positive. So this chart summarizes our discussion. I've just included a few graphs here to help us remember the first derivative test by visualizing it with these graphs. Here's C, our critical number. Slope of the tangent lines to the left of C are increasing or positive, and to the right of C they are negative, so it's decreasing, so we would have a local maximum. For this graph, we have a critical number at 2.5. We analyze the slope of the tangent lines to the left of C and to the right of C, and we can see changes from decreasing to increasing, so we would have a local minimum. Now here's a graph. We would get a critical number here. The slope of the tangent lines to the left of C are increasing, but they continue to increase after our critical number. So we don't have a local maximum or a local minimum. And likewise for this graph, we would have a critical value at C. To the left of C, the slope of the tangent line is negative, and to the right of C, the tangent line is negative. So we do not have a relative maximum or minimum at that value. Find the local maximum and minimum values of the function. Now this is summarizing what we did earlier, and this is in table format. So we can see the derivative changed from negative to positive, so we would have a relative minimum. Then the graph changed from positive to negative, so we would have a relative maximum. The derivative then changed from negative to positive, so we would have a local minimum. And if you analyze that, looking at the interval from 0 to 2 and then greater than 2, we were decreasing on the interval 0 to 2, then we changed to increasing, so there must be a local minimum. Find the local maximum and minimum values of this function. So if we're just trying to find the local maximum and minimum values of the function on this interval, we know we can find local or relative max and mins by setting the derivative equal to 0. So let's find the derivative of our function. So we'll set this equal to 0. And when we solve for cosine of x, we would subtract 1 and divide by a positive 2. So we'd have negative 1/2. And if we looked at our unit circle, we know that the cosine is negative in quadrants 2 and quadrants 3. Now the cosine of what angle equals 1/2? Well, if we used our reference angle, we know the cosine of pi over 3 is positive 1/2, so that would be our reference angle. Now the reference angle is always between the x-axis and the terminal side of the angle. So if we wanted to find this angle, we would use our reference angle, which is that angle between the terminal side here and the x-axis. That would be pi by 3. So we would take pi minus pi by 3. Get our common denominators. We can see x equals 2 pi over 3. Now, using our reference angle, we know we're going to have an angle in quadrant 3 also. So this angle right here would also be pi by 3. So we would take pi plus pi by 3. And getting our common denominators, we'd have 4 pi by 3. So there we have our critical values. Now let's set up our number line. Both of these critical values fall within our interval 0 to 2 pi. So let's say this is 2 pi by 3, and this is 4 pi by 3. So our intervals would be from 0 to 2 pi by 3, 2 pi by 3 to 4 pi by 3, and 4 pi by 3 to 2 pi. Those are our intervals. So now we're going to choose a value within those intervals. And let me make a notation over here on our, this is the angle 2 pi by 3. So we could choose any value. Let me erase some of this so it doesn't look so cluttered. So we could choose any value on that interval. I see this value here would be between 0 and 2 pi by 3, which is pi by 2. So if we plugged pi by 2 into our derivative function, here's our derivative, we would have, now this is for pi by 2, so we would have 1 plus 2 cosine of pi over 2. Now we know that the cosine of pi by 2 is 0. So 2 times 0 is 0. So we'd be left with 1. So we are plugging into our derivative pi over 2, and we got a value that is positive. So we know it's increasing on this interval. The next interval, let's look back at our unit circle. Now here's the angle we're working with. From here all the way over to here, that's our angle now. That's our 4 pi by 3. So we're going to be between 2 pi by 3 here and 4 pi by 3 here. And I'm going to use pi. That seems most convenient. So here's where x equals pi. So if we plugged in pi, we'd have 1 plus 2 times the cosine of pi. And we know the cosine of pi is -1. So we'd have -2 plus 1. So we get a negative value when we plug in pi. So we would be decreasing on this interval. Let's look for a value between 4 pi by 3 and 2 pi. Now, if this is 4 pi by 3 here, this angle here, and here is 2 pi let's choose 3 pi by 2. So if x equals 3 pi by 2, we'd have 1 plus 2 times cosine of 3 pi divided by 2. And we know the cosine of 3 pi by 2 is 0. So again, we get positive 1. So this would be a positive value. So we are increasing on this interval. So we have determined where this function is increasing and where it is decreasing. We can also determine if we have any local max or mins, and that's what the question is asking us to find. Find the local maximum and minimum values of the function. So on this interval from 0 to 2 pi by 3, it's increasing, and then it changes to decreasing, so we would have a local maximum. Now the next value, we are decreasing from 2 pi by 3 to 4 pi by 3, or decreasing, but then we change to increasing, so we would have a local minimum. And here's the table that shows where the derivative is increasing or decreasing and the intervals. And then we could analyze this to determine if we have local maximums or local minimums. Here's our graph, and we can see that at the values we found our local maximum and minimums at 2 pi by 3 and 4 pi by 3, we have our local max and local minimums. Next time we're going to be looking at how does the second derivative affect a graph.